Okay, today's lesson is 3-3 called Optimization with Linear Programming. Sometimes it is actually just called linear programming, and sometimes it is called linear optimization. It is a method for finding minimum or maximum values of a function over a given system of inequalities, with each inequality representing a constraint. Now, the vertices of the solution set, called the feasible region, are substituted into the function to find the minimum or maximum value. So here's a picture of what the problems are going to look like. We're going to have two different types of feasible regions. Basically, one is either enclosed or what we refer to as bounded, or one could be unbounded, okay, because it goes on forever and ever in one place. So, as we just mentioned, this shaded region is called your feasible region, okay? The inequalities, the systems of inequalities, are called your constraints. And then the corners, the vertices of the region, each one is called a vertex. So all of those are inequalities. So when you're doing these things, here's two examples of bounded regions, okay? And I color-coded it. I'm trying to go through this very quickly. Some of y'all might need it, some might not. Please email me or come to email me if you have any questions about anything. Okay, so we have three inequalities here. I hope you remember that x is a vertical line. So this says x has to be between -2 and 6. I got -2 and 6, and it has to be in between those two lines. Y is between 1 and 5. So here's y equals 1, y equals 5. I'm shading in between those. And then I graph this, which is not horizontal or vertical. So the key information I need is that its y-intercept is 0, 3, and its slope is 1. So I graph that, and it's an inequality, which we've talked about, means shading. And when y is by itself, which most of the time it will be here on the left side, I can go with the fact that y is less than. So I go find my y-intercept and shade below my y-intercept, which makes this our feasible region. Okay, now we are supposed to find the maximum min values. So the work that I want to see you do when you do these problems is to set up a chart. Keep in mind also, when you look at these problems, y'all, anything that is an inequality is graphed. If it is not an inequality, that's what is called the objective function. And you do not graph that. That's the one where we're going to go to our shaded region, A, and find the vertices, A, B, C, and D. Those were pretty clear cut because of horizontal and vertical lines. And we're going to take those coordinates and plug them into the feasible region. And this is what I want the work to look like. Okay, so you show me the points. Here's my objective function. I don't care if you show me all of this, but I do expect to see what value I get for each region. It is important that I see all of the vertices of the region, even if you know it's not an answer to your problem. Okay, so in this particular case, if I'm looking for a max or min, clearly you can see that 12 is a max and -28 is a min. And in case you didn't see that, because sometimes the pointer on my stylus does not point, this is the work that is optional. Minimum would be for you to list the coordinates and give me the value when you plug them in. That is the minimum amount of work I expect to see. So to answer this question, find the max and min values for each region. Okay, the value, y'all, is the y function of the variable. So the minimum value is -28. Where does it occur? At 6, 1. Okay, the maximum value is 12 at -2, 1. Okay, so I did another example over here for you. Here is the table of values that support the work. I'm looking at my answers, and there is clearly a min at -48 and a max at 24. So when I answer the question, if I asked for the minimum value, then you would tell me it's -48. If I asked where it occurred, then you would tell me at -4, -6. Okay? Okay, so those are two bounded regions. Here are two unbounded regions. I did the same thing for you, color-coded the graphing of the lines so that you can hopefully follow along easily. I wrote down the key information for graphing anything that was not horizontal or vertical. My vertices, I have two vertices, A and B. I put them in a chart for you. Again, minimum would be for you to tell me what the points are and tell me the values. And here I have a max. 52 is not a min, y'all. Why is it not a min? Because this is an unbounded region. So there is no true minimum. It goes on forever and ever. Excuse me, this pollen. So your answer would be maximum at -4.8 is equal to 88, and there is no minimum. Okay? And on this side, again, color-coded the lines. Excuse me, none of them are horizontal or vertical. So again, I'm giving you key information, y-intercept and the slope, y-intercept and the slope, and apparently I forgot to write the y-intercept and slope here. So here I have 0, -4, and it's not writing very well, and the slope is again -4, which is why I know these two lines are going to be parallel, because they have the same, it's the purple and the blue line are going to be parallel because they have the same slopes, different y-intercepts. And if you have any question here, 16 is way up here, y'all. But if I know my slope is -4, I can start up at 16. And if I go down 8, then I have to go over 2, because that simplifies to -4. So that's where my first point was. Okay. Found my vertices A and B, put them into a chart. And which one? Okay, so when you look at your graph, this, hopefully you see, has no max. It'll have a min, but no max. And which one of these is a minimum? Of course, that is -46. So you would write your answer as a minimum equals -48 at 1, -8. Okay? All right, so the last thing that we have to do is talk about the fact that this is actually the kind of problem that is very applicable in the real world. Okay? They use it. I am showing you a very simplified process of it. But with computers and all that we have today, you can have an infinite set of constraints to apply to your situation. Obviously, you don't need an infinite, but so this is where the true optimization comes in. To optimize means to find the best price or amount to to minimize the cost or maximize profits. That's what optimize means. So optimization with linear programming, you're going to first identify your variables. And the best way to do that is to look to answer the question in your word problem. Then you're going to write a system of inequalities, graph that system, find the coordinates of the vertices of your feasible region, write a linear function to be minimized or maximized, then substitute those coordinates into the vertices of your function, and then select the greatest or least result. Make sure that you answer the problem. Okay, so here's an example. This is the last problem. Each week, Mackenzie can make 10 to 25 necklaces and 15 to 40 pairs of earrings. If she earns a profit of $3 on each pair of earrings and $5 on each necklace, and she plans to sell at least 30 pieces of jewelry, how can she maximize profit? So the first thing we're supposed to do is identify the variables. Okay, I'm going to use the letter N for necklaces and E for earrings, just because in word problems, it helps me keep the information straight. If everything's X and Y, I kind of tend to get a little confused. Okay, the next thing I'm supposed to do is write a system of inequalities that goes with my problem. Okay, this says she can make 10 to 25 necklaces. Well, that means that N is going to be between 10 and 25. She can make 15 to 40 pairs of earrings. So E is going to be between 15 and 40. The next one, she plans to, if she earns profit, so this is my objective function here. If she earns profit and I'm trying to maximize the profit, this is the one that's going to be my objective function. So I'm going to go to this last piece of information. She plans to sell at least 30 pieces of jewelry. So I have N plus E has to be greater than or equal to 30. Now, you can see that I've already graphed it here, but one of the things that I want to remind you, when you do this and you choose the variables, I can't encourage you enough and tell you to write an ordered pair so that you keep straight which one's going to be X and which one's going to be Y in your problem. Okay, so if you write it like this, then I know that E has to go on my x-axis and N has to go on my y-axis. It does not matter which way you write this. I'm just telling you to write it so that you can keep your information straight and all the numbers in your problem straight. So we graphed N. N is horizontal, is the vertical axis, and that means that my measurements are going to be N being between 10 and 25. Okay, because remember, if this was Y, then these would be horizontal lines. So that's 10 and 25. X or E is between 15 and 40. Okay, and then to graph this, it's in standard form, which means the easiest way to graph it is to find your intercepts, not to deal with the slope. So my intercepts are 30, 0, and 0, 30. So I plotted both of those. And we plug in 0, 0. 0, 0 is not greater than 30. So that means I'm shading on this side of the line, which is why this becomes my feasible region. Okay. And then once we've done all that graphing, this last one, my profit equation, she's going to earn $3 on each pair of earrings and $5 on each necklace. So I go and find my vertices, which I have labeled A, B, C, D, E. I put them in my chart, and then I'm looking. I want to maximize profit. So which one of these numbers in the last column under dollar signs is the largest? And that, of course, is $245. So Mackenzie should make 40 pairs of earrings and 25 necklaces to maximize the profit. So I've answered the question. So that was real quick. You can speed me up if I'm too slow. You can slow me down if I'm too fast. But more importantly, email me or come see me if you have any questions. Thank you very much, and I hope you all have a great day.